In the previous video, we have successfully implemented the push functionality, which will basically add the new value at the end of the singly linked list, right? In this video, let's try to perform an operation which will basically delete the very last node we have inside the singly linked list. So that operation is nothing but pop operation. So we already know the very last node is nothing but the tail node we have inside the singly linked list, right? And we have to delete that node from the singly linked list. That basically means that inside the singly linked list representation that we are maintaining, right, we are maintaining the head node and tail node. Along with that, we are also maintaining the length of the singly linked list. So we have to make sure that we are making proper adjustments in these three variables according to the cases that we are seeing. Here, one thing that you have to remember is basically deletion doesn't mean that we are actually freeing up the memory. So what exactly we mean by deletion is in the case of singly linked list, right, every node will have the reference of the next node, right? That means if you take the reference of the node true, it will be available inside the node with the value code. Similarly, the reference of the code will be available on the node 10. Similarly, the very last node we have inside the singly linked list is false, right? And this reference will be available inside the node -10. So to delete the node false, that is the very last node we have inside the singly linked list, what exactly we will do is the next that we have inside the node -10, that we will update it with null if you are following Java or JavaScript based implementation. In the case of Python, we will update it to none. Okay, so in that way we are losing the track of the very last node because we have deleted the reference. That means that that node is no longer available inside the singly linked list. And remember that since we are deleting the very last node, whatever the tail node that we had previously will no longer be the tail node. We have to update the last but 1th node as the new tail node of the singly linked list. Okay, so that is a simple way how we actually delete a value inside the singly linked list. What exactly are the different cases that could appear when we are trying to perform the pop operation? Let's assume that user is trying to perform the pop operation on a empty singly linked list. That means that there are no nodes at all inside the singly linked list. That means both head and tail are empty and length is 0. In that case, obviously, since we don't have any values, we will not be able to perform pop operation. In that case, we will simply return null if you are implementing Java or JavaScript based representation, and if you are following Python based representation, we will simply return none. Okay, so that is the first case. In the second case, where we have only one node inside the singly linked list, in that case, since we have only one node in the singly linked list, right, let's assume that only one node is 10. So obviously head will be pointing to this node and we will also have the tail at the same node, right? So the only node is available inside the singly linked list and we have to delete that only one node, because as part of the pop operation what we do, we will delete the very last node. When we have the only one node inside the singly linked list, pop operation, we will have to delete that only one node. In that case, since we are deleting this, the singly linked list will become empty. So how will we exactly represent an empty singly linked list? To represent that, head we will update it to null or none. In the case of Python we use none. In the case of Java or JavaScript we will simply use null. Similarly, the tail also we will update it to the similar way how we have updated in the case of head. And there are no values inside the singly linked list at all, right? In that case we will simply update the length to 0. So in that way we are making sure that there is no inconsistencies in the head or tail or length that we are maintaining for representation of a singly linked list in our implementation. And the third scenario is obviously we have more than one node. So if we have more than one node, this is the classic example, right? So in that case, head will be somewhere and tail node will be somewhere. So we have to make sure that we are deleting the very last node. So how will we actually delete is, let's take a small example where we have, let's say, 3 nodes available inside the singly linked list. So this is the head node and this is the tail node, and let's assume that 10 code and true are the values present inside the singly linked list. So according to the algorithm that I have explained, how will we delete the last node? We will simply go to last but one node, that is we will go to the node code, and there we have the reference of the true inside that node, right? And we will simply assign it to null or none based on the choice of the programming language that we are using. Okay, so as part of the first step, our aim is to reach the last but one node, and there we will update the next to null, and whatever the node that we have deleted, right, in that way we are losing the reference of the node true. So the connection has been removed. As a result, the value has been lost from the singly linked list. But the thing is, the tail is still available at true only. So, and that is not part of the singly linked list. So we have to make sure that last but one node is becoming the tail node. That's why in the case where we have more than one node, we will go to the last but one node. There we will update that nodes next to null or none based on the choice of the programming language that we are using, and we will basically decrement the length by 1 because we are deleting the node after all from the singly linked list, and we have to make sure that the tail node is getting updated to last but one node. Okay, so that is the process of performing a pop operation on a singly linked list. I hope you understood. Now let's write the pseudocode for the same. So to write the pseudocode, obviously first what we will do is we will write a function called pop function. Obviously it will not take any argument, and it will basically delete the very last node, and it will return that node back to the user. So as part of the first step, what we will do, we will check if the singly linked list is empty. If it is empty, what we will do, we will simply return null or none based on the choice of the programming language that we are using. So this is the case where we have the singly linked list is empty. The second case is where we have only one node. That means if the length of the singly linked list is 1, that means whatever the length variable that we are maintaining, right, if the value inside that is 1, the singly linked list has only one value. Besides this, one more comparison that you can do for checking if the singly linked list has only one value or not is because when we have only one node inside the singly linked list, head will be at the same node and the tail will also be at the same node. So you can simply do head is equal to the tail as well to check if the singly linked list has only one value or not. If at all, if that condition is matching, how we will delete the last node? We will simply update the head that we are maintaining. We will simply update it to null or none based on our programming language of choice for implementation, and inside the tail that we are maintaining, we will also make it as null or none, and the length will become 0 because there are no nodes inside the singly linked list after deleting. But in the end we have to return the node that we have deleted, right? But that's why before performing or updating the head to tail to none, just read the tail node, okay, and store it in some variable. In the end, return that old tail. Okay, so that is the case where we have only one value inside the singly linked list. Now let's just try to perform the pop operation on a singly linked list where we have more than one node. So otherwise, so the logic will be simply otherwise. That means that we haven't matched the first two cases. That means that we have more than one node inside the singly linked list. So in that case, what we will do, we will go to last but oneth node. So first process is to check read the last but oneth node. So we will start at the head node and we will keep track of the previous variable, and using that previous variable we will go to the last but oneth node. Once we go to that node, right, how will we delete the last node? We have the reference of that node in the last but oneth node, right? That is available in the next of the last but oneth node. So we will update next to, we will simply update it to null or none based on our programming choice of implementation, and we will simply update tail to last but oneth node, because the reference of this node has been lost in the last but oneth node because we have updated it to null or none. So this will no longer be the tail node. So we have to make sure that tail node is getting updated to the actual tail node or the very last node we have in the single linked list, which is nothing but the last but oneth node. And here we will again decrement length by 1, because after all we are deleting one value from the single linked list, right? So since that value has been deleted, we have to make sure that we are making proper adjustments in length as well. Since we are deleting one node, we will decrement the length also by 1. In the end, just like how we read the tail node, we will first read the tail node here in this case as well, so that in the end we can return the old tail of singly linked list, which is actually getting deleted from the singly linked list as part of the pop operation. So this is the pseudocode for implementing the pop operation on a singly linked list. So just remember that there will be 3 cases. First case will be empty singly linked list, and the second case will be where we have only one node inside the singly linked list, and the third case is where we have more than one node. So according to that case, we are handling and we are making sure that head, tail and length which we are maintaining in our single linked list in presentation are getting adjusted with the proper values. Okay, now that we have seen the pseudocode, let's convert this into our programmatic implementation. Okay, so inside the singly linked list implementation that we have written, beneath traverse function, let me just write a pop function. So as part of this pop function, we are trying to remove the existing tail node. So ultimately we would want to return the tail node. So what the function signature would be public, the return type is node, and the pop function name is pop. Okay, so inside the pop condition there are basically 3 cases, right? When you are trying to perform the pop operation on an empty linked list, and you are trying to perform pop operation on a singly linked list which has only one value or one node, and the third case is where you are trying to perform the pop operation on a singly linked list that has more than one value. Okay, as part of this implementation we need to write the logic in such a way that we are going to handle these 3 cases. So as part of the first case, what I will do is I'll basically check the case where there are no nodes at all. That means basically you can check if length is 0, or if the linked list is empty, both head and tail will be pointing to null. So based on that, I'll simply say this dot head equal to null. That means there are no nodes in the singly linked list. In this case, since there are no nodes in the singly linked list, we can't delete the tail node, right? In that case, we'll simply return null. If this is not the case, that means we might have a singly linked list where we might have only one node or more than one node in the singly linked list. So to support these 2 scenarios, what I will do is I'll simply take an else block, and I inside else block, or else you can simply do else if block also. Here, if inside the else if block, to handle the case of where we have only one node in the singly linked list, when we have only one node, what we will basically do, both head and tail will be pointing to the same node. So based on that, what we can do again, if this dot head is equal to the this dot tail, that means if both head and tail are same, then we need to delete the tail node or head node also, because only one node is there. So if we delete the existing node itself, then the head head of the singly linked list should be pointing to null, and the tail of the singly linked list should also be pointing to null, and the length should become 0. Okay, these three cases we need to handle. Okay, but along with this we need to return the node that we have deleted, right? So just to return, let's just read it into some variable. Let's say tail node equal to this dot tail. Either you can take this dot head also. In the end we need to return tail node. Okay, so we have successfully handled the second scenario also, where we have only one node in the singly linked list. In that case, both head and tail we have assigned to null, indicating that linked list is empty, and length also we have updated to 0. Now we need to handle the third case. So third case is where we have more than one node in the singly linked list. In that case, if we try to remove the last node, which is tail node, whatever the node that is previous to the tail node, right, that node should become the new tail node of the singly linked list. And from that node, if we simply update the next to null, we would simply delete the existing tail node of the singly linked list. So to do that, what I will do is I'll simply take node current. I'll simply take current tail. This can be accessed from this dot tail. Okay, now what I will do is, now I'll also define another variable called node new tail. Okay, so this will be in the beginning. I will assign it to the head node. Okay, in the iterative operations we need to go to the last but oneth node, right? So now we will write that logic, while we will also define one more variable called current node. Node current node equal to this dot head. So we are basically starting from the head node. We need to go to last but oneth node. Once we reach that node, we will simply update the next of that node to 0, and we will make that specific node as a tail of the singly linked list. Thus we are removing the existing tail node. So as long as this current node is not equal to the current tail node, what we will do, we'll simply update the new tail to current node. Okay, in this way we are simply keeping track of the previous node that we have traversed, which we have inside the variable new tail. Similarly, to move on to the next node, what I should do, I'll simply update the current node to current node dot next. Okay, using this we are keeping track of the previous node inside the new tail variable, and we are also moving on to the next node by updating the current node to current node dot next. Okay, once this while loop completes, whatever the new tail variable we have, right, in that variable we will be having the last but oneth node on the singly linked list. So what we will have to do there, we will simply need to new tail dot next, we will simply assign it to null. Okay, that means whatever the last node we have, that is tail node, we have deleted that, but simply applying the next of the previous node to the existing tail node to null. Okay, so here we have deleted the current tail node, but if you see the logic here, right, the new tail node of the singly linked list is inside the variable tail node. So we simply need to update this dot tail should be pointing to new tail. Okay, along with that, we removed one node in the singly linked list. That means we should reduce the length by this dot length should be decremented by 1. Okay, this is how, sorry, while current node is not equal to current node, I did current node is not equal to current tail here. Okay, this is because whatever the node that we are processing, we should go to last but oneth node. That's why once I reach the tail node, I will not run this logic anymore. So I will have the access to last but oneth node inside the new tail variable. Okay, so here we need to return the node that we have deleted, which is inside the variable current tail. Okay, we will simply return current tail. Okay, so this is the pop implementation. If you observe here, we've handled three cases where there are no nodes in the singly linked list at all, where there are only one node, where there are more than one nodes. Now let's simply uncomment these and let's try to perform pop operation. So SLL dot pop. If we simply pop this inside the singly linked list that we have declared here, the head is 10 and the tail is minus 10.0. So if we perform the pop operation, the tail node should get deleted and the new list should be 10 codingpal.arg and true, and 10 should be the head and true should be the tail of the singly linked list. So if we simply execute this line of code, and anyway we are we are performing the traverse operation, right? Once we pop it, so we will simply run as Java application. If you observe here, we have got the output 10 codingpal.arg and true. Okay, this is a case where we have more than one value in the singly linked list. Similarly, let's try to perform the pop operation on a singly linked list where we have only one node. Now if I run it, see, we haven't seen anything in the console because whatever the node that we have, that itself we are deleting. So head and tail will be pointing to null. So when we call the traverse function, there will not be any nodes, right? So it will not print anything. Similarly, if I remove this node also, obviously whatever the node that we are processing, it itself is like an empty linked list, right? If I execute it again, it should not print anything. Okay. Similarly, if I have only two values inside the singly linked list, in that case, it should delete codingpal.arg and both head and tail should be pointing to the same node, that is 10. So if I run as Java applications, okay, you see 10. Okay, if at all if you want to print the head and tail values also, you can do sysout sll.head.value plus sll.tail.value. This will basically print the head value and tail value we have in the singly linked list. So if I simply run as, both head and tail are at 10 only. So traverse is printing first 10. As part of the second print statement, whatever the head and tail we have, we are printing that. Similarly, if we add three values also, the scenario, the head should be 10 and the tail should be codingpal.arg. Okay, so that is the output that you have got. Okay, this is how we implement the pop operation in a singly linked list using Java. Okay, all right. Now we have already implemented the pop operation as well, right? In this video, let's try to understand time and space complexities involved in the pop operation. So obviously, let's just try to divide it into best case as well as the worst case scenarios for both space and time complexities. So when will the best case of pop operation will actually occur? When the singly linked list is empty or it has only one node inside the singly linked list, because we don't have to go to last but one node inside the singly linked list, right? That's why the best case will obviously occur at when we have only one node in the singly linked list or empty single. In that case, what exactly we are doing? In the case of empty, we are simply returning null or none based on our programming language of choice. In the case of when we have only one node, we are updating the head node with the null or none and tail node with the null or none, and length also we are decrementing by 1 or we are making it to 0. So obviously all these operations are simple assignment operations, right? And these assignment operations will take 1 unit of time. As a result, in the best case scenario, the time complexity will be order of 1. Okay. Now let's talk about the worst case scenario. Let's assume that the singly linked list is that we have on which we are trying to perform the pop operation is something that like you see on the screen, where let's just assume that we have n number of nodes, right? In that case, what exactly we are doing? We are going to last but one node. That means we have to start at the head node and we have to go to last but one node. That means that we have to run a loop for going till the last but one node. That loop we are running it for n minus 1 number of times, right? So in that case, Once we go to that node, we are updating the next appropriately so that the last node is getting last. And after that, we are updating the tail to null or none. So obviously, the overall time complexity in the worst case where we have n number of nodes, the major operation is to go till last but one node. For that, we are running a loop and it is running n minus 1 number of times. As a result, we can say the time complexity will be order of n minus 1, which is nothing but order of n as a worst case time complexity for pop operation. Okay, so that is something that in terms of time. So let's talk about in terms of space. So we already have the head and tail and length inside our singly linked list representation. So in the best case scenario, when we don't have any values at all, or when we have only one value, we are simply updating the head with null or none, and similarly tail also getting updated with null or none, and length we are updating it with 0. And these are simple assignment operations, right? And obviously assignment operations will not take more than unit amount of memory internally. As a result, in the best case, the time space complexity will be order of 1 only. Okay, now in terms of worst case space complexity, yeah, we are sure that we are running a loop for n minus 1 number of times, but we are taking a help of a single variable for keeping track till the last but 1th node. We are simply using a single variable, and that variable itself is keeping track of the previous node. In that way, we are going to last but 1th node. Obviously, since it is a single variable, it will take constant amount of memory. And after that, the tail node is getting updated to last but 1th node, and length is also getting decremented by 1. These assignment operations will obviously take constant amount of memory only. As a result, the overall space complexity in the worst case also, where we have more than one node, or where we have n number of nodes inside the singly linked list, even though we are running a loop for n minus 1 number of times, the space complexity will still remain constant only, because we are simply using a single variable for going till the last but 1th node. Okay, so that is the space complexity in the worst case scenario for performing the pop operation on a singly linked list. Okay, so that is how we calculate the time and space complexities, and that is how we exactly implement the pop operation for various cases that can come while implementing. Okay, in the next video we will get on with implementing the next functionality on a singly linked list. Okay, I'll see you there.